speaker, Jessica Agarwal. She did her PhD here in Heidelberg in 2007 about Grün at the Max Planck Institute for Kernphysik. And then spent some time in Aztec, in Noordwijk in the Netherlands, working, among other things, on Rosetta, and also starting an own research project on active asteroids, which is actually the topic which she's going to talk about today. Then she spent time as a postdoc in Potsdam, and now she works at the Max Planck Institute Max Planck Institute für Sonnensystemforschung in Göttingen, where she also works, among other things, on this topic of active asteroids. Now, let's welcome her to Heidelberg and look forward to it.
Thank you very much for inviting me to your colloquium. I'm happy to tell you about active asteroids and give you an overview of what we did in the last years on this topic. I'll first give you an introduction to actually what are active asteroids. Then I'll briefly explain you what we can observe of them and which methods we use to study them. Then I'll talk about a few individual objects and about their peculiarities, because they are very different. And finally, I'll try to put our findings into a wider context. Try to find a more common topic. Asteroids. So you know the classical picture of small bodies in our solar system, those comets and asteroids. The comets are rich in volatiles. They have recently entered the inner solar system from the Kuiper belt, so they have conserved ice from the early solar system. And when they approach the sun, they are heated, the ice sublimates and carries with it the embedded dust, and then the comet forms these beautiful structures that we all know that characterize a comet, and that right now we can see in wonderful detail with Rosetta on the left side here. Asteroids, by contrast, usually are thought of as pieces of rock or rubble piles of dust or pebbles, but the surfaces usually are inert. We just see black sky at the horizon of this asteroid. And if you look at them from further away with a telescope, the comet displays this long characteristic tail of dust particles carried away by radiation pressure, whereas an asteroid usually is just a point source. Now, active asteroids look like comets. They are not point sources, but they have dust tails which are similar to comets, or at least some of them remind of comets. This one is the prototype, Ernst Pizarro, which was discovered almost 20 years ago now. And here we have a collection of other more recently discovered active asteroids, which are, you see, they are very different. We have this one with this arc-shaped structures. We have this one which has multiple tails. We have one that broke up completely. But you also have the really comet-like classical dust tails. So why are they not just comets? The difference is they have the orbits of asteroids. So this is a plot of small bodies in the solar system. The eccentricity of the orbit is plotted versus the semi-major axis. And you see this blue cloud here, they are the comets. And you have the orange dots, which represent the asteroids. This line displays orbits that have the aphelion and the perihelion of Jupiter's orbit. So everything to the right of this line crosses Jupiter's orbit, which makes the orbit unstable in longer time scales, because Jupiter disturbs the orbits of the comets. And this line notes orbits that always stay outside the orbit of Mars. So everything to the right of this line never encounters Mars. So in this triangle, we have very stable orbits that encounter neither Mars nor Jupiter. And this is where you find the main asteroid belt. These bodies have very stable orbits. They probably have been there since the formation of the solar system. And this is why usually they are inert. They are also comparatively close to the sun, so it is hard to understand how ice could survive there for such a long time scale. And still, all these red dots you see, they are the active asteroids. They clearly have the orbits of typical asteroids, but they don't look like asteroids. So the question is now, what causes their activity? Is it similar to comets? Is it something entirely different? And this is, well, I'll try to find some answers to this. Before I go to the results, I would like to explain to you what we can actually observe of the active asteroids and which methods we use to analyze our data. The nucleus, as I said, usually is a point source. So basically we can measure its magnitude, its visual magnitude. And then we know the distance of where it was, and we know the phase angle, and we have a reasonable idea of its albedo, so we can infer the size of the nucleus. We can infer its cross-section and calculate an effective diameter. So we know most active asteroids have nuclei between 100 meters and 2 kilometers. So they are really quite small. The other thing we can measure the nucleus magnitude as a function of time. So here we have a time series of about 7 hours, and you see it changes periodically. And this is because the nucleus is not a sphere, it's ellipsoid or more complicated shape. So when it rotates, you see the cross-section changing. And from this light curve, we can infer the rotation period. And this is something that would be very interesting for our future results. The dust tells us also a lot of things. The motion of dust is close to the nucleus, determined by a lot of forces, different forces. First you have the nucleus gravity, you have centrifugal forces, if the nucleus rotates fast. If there's ice sublimation involved, you have the gas drag. If there's an impact, of course, you have the impact forces. So close to the nucleus, the motion of the dust particles is complicated, and it's also not resolvable to a ground-based telescope normally. Most of this happens inside the central few pixels of HST. But after the coupling to the nucleus ceases due to the distance, then the motion of dust particles is determined only by the initial velocity the particle had on decoupling from the nucleus, by solar gravity and solar radiation pressure. And this makes models of the dust motion manageable. So we can constrain the initial conditions of ejector from the nucleus from the way the dust moved later on. A little bit about the solar radiation pressure. Radiation pressure follows an inverse square law with heliocentric distance, just like gravity. So if you calculate the ratio of radiation pressure and gravity, there's no dependence on heliocentric distance anymore. This ratio depends only on the property of the particles, basically on its cross-section to mass ratio. And if you assume that all particles have a similar density, then the ratio between radiation pressure and gravity is uniquely related to the size of the particle. And this ratio we call beta. And this means that basically the radiation pressure acts on dust like a mass spectrometer. Small particles are blown away very quickly, whereas large particles stay close to the nucleus on longer time scales. And to describe the motion of dust particles under gravity and radiation pressure, we can write down an effective potential. It's still the central potential, it has the same form as the gravitational potential, but the gravitational constant is reduced by this beta parameter. Now, if we have a comet's tail or an asteroid's tail, we we can connect the location of a dust particle to its origin, to the time when it was ejected, and to its size. So you have the nucleus here. This is the direction towards the sun. This is the direction where radiation pressure blows the dust. And then you can just calculate for a given observation time, geometry, where particles would be that were ejected on a given date, and which have different sizes. And you find that they lie in more or less straight lines, and we call these lines synchrones. This is why all these straight lines are marked by dates. And we can do the same for particles of the same size, but ejected at different times. And we call these lines synchrones. And these are usually curved. So synchrones and synlines form like a grid on the sky. And you know, if you have dust, for instance, here, you know it was ejected between April 10th and April 7th. So this is how you can, if you see a comet's tail, to a first approximation, you can get an idea how old it is and what kind of particles it contains. If the initial velocity is not negligible, then things become more complicated, but even then, this gives you a rough idea and a first impression. So this concept we use very much to understand what happened to the active asteroids when we discover them, because usually then they already have that tail, and we have to find out in which respect what made the tail appear. And one quantity that we use very often is the position angle on the sky of a synchrone and of the tail. That's the angle between the synchrone and the projected orbit, because it's uniquely related to the date of ejection. So if we measure this position angle, then we can say something about the date of ejection. Now the first group of objects I want to talk about are the so-called main belt comets. They are the classical active asteroids, the so-called prototype. They contain also 133P Pizarro, the object that was discovered first. And they have some common properties. One of these properties is that they show protracted activity, like comets. The activity continues for several months typically before it dies down again. And in order one way to derive this is just what I explained before, the synchrone and sunlight plots. You have here an image of one of the main comets. You have the nucleus here, and you have dust to both sides of it. And then we make a synchrone and sunlight plot, and we find that dust that was ejected, say, before September, is to the west of the nucleus, whereas dust ejected later is to the east of the nucleus. And since we see that there's dust to both sides, we know that it must have been active both before and after September. And then we can even measure the angle between the tail and the projected orbit and say something about when the activity actually started. So we know that this one has been active for several months. Another common property of at least a few of the main belt comets, of 3 of them, is that they have confirmed repetitive activity. So the activity returns every orbit close to perihelion, just similar to the comets. So these are observations taken in 3 different perihelion passages. This is from 1996, 2002, and 2007. And whenever the dot is colored, the object was active. And all the way out here, it was inactive in between. This is usually thought to be a very strong sign that the cause of the activity can be ice sublimation, because ice would sublimate preferably when the object is close to the sun, because it is warmer there. The third common properties of main belt comets is that they do not seem to emit significant quantities of millimeter or centimeter sized particles. So the bulk of material ejected from them is on the order of 100 micron typically. Whereas in comets you find also centimeter sized particles. And in some of the other active asteroids you find this as well. And also this indicates that sublimation is a possible cause of the activity in these objects, because sublimation, gas drag, probably accelerates small particles which have a high cross-section to mass ratio. Whereas larger particles are more heavy, and for a weakly sublimating source, it is impossible to accelerate them. So to summarize, the classical main belt comets most likely are driven by the sublimation of ice, because they have protracted activity, they have orbitally repetitive activity, and they have this absence of millimeter-sized debris. Now I come to another active asteroid that is very different, which was discovered in 2010, called A2. A2 had a tiny nucleus, 60 meters in radius. You see it down here. This is an HST image, so it's really high resolution. And the nucleus was almost detached from the tail, and the tail was led by these cross-shaped arcs of large debris, and then consisted of smaller debris all the way out. What happened here? This does not look like a classical comet. So we got 8 HST images over a series of 4 months, which allowed us to follow both the relative positions of the fragments and the position angle on sky of the tail. And then, coming back to the synchro-syncline analysis, we calculated synchros for all our observation dates and plotted the position angle of a given synchron as a function of observation time. This is what you see here. So you have these, each color denotes one date of ejection. This is the observation time, and this is the position angle on the sky. So the synchron of, say, May 21st, the red one, would evolve, the position angle would evolve from down here, up there, and back again. And then we calculated this for a series of different ejection dates, and we plotted the observed position angles on this. And we see that all the observed position angles match a single synchron. So this tells us that the activity was more or less instantaneous, maybe less than 2 weeks at least. So it's very different from what we saw before. This did not take place for months, because then the tail would have looked entirely different. This angle would not have been following the same synchron all the time. So we know it was a very short event. The other thing we found is that we followed the motion of the fragments in this cross. So we looked for the more pronounced regions. I don't think they're real hard fragments, but rather like clouds, denser clouds of debris. And we looked for their positions in all the images. And then we ran models with test particles and tried to find how you have to eject a particle that it follows the motion of these fragments in the way we saw. And we find that the ejection velocities of dust in these regions lie in a plane. So you have here the x and y component of the ejection velocity. These are the components in the orbital plane of the asteroid, and this is the perpendicular component. And you see that the projection is a line. So the original velocities lie in a plane. And in addition, we find that the velocities are tiny. They are on the order of 0.1 meter per second, and the escape speed from the 60-meter nucleus is also 0.1 meter per second. And the third finding is that there definitely was centimeter-sized debris involved, because 3 years later, we still could find this really bright trail of very large particles on the orbit of the asteroid. It was not active at this time, there was no trace of a coma, it was a point source, but the debris remained. And it must have been a large degree because otherwise radiation pressure would have blown it away. So to summarize, the question is what caused this to happen? Was it also sublimation of ice? And there are several reasons why we think this is unlikely. First, the asteroid is really tiny, 60 meters, and it is close to the sun. It's in the inner main asteroid belt. So in this region of the asteroid belt, it is very unlikely that ice can be conserved over the age of the solar system inside a 60-meter body. And in addition, the short duration is very untypical for sublimation of ice. On the other hand, if it was an impact, this would be perfectly consistent with the short duration and also with the ejection of large debris. However, we see this absence of fast ejecta. All the ejecta were on the order of 0.1 meter per second and 0.2. So all the ejecta we saw had velocities on the order of the escape speed of the body. So we think that typically a high velocity impact should create also faster ejecta, which we did not see. So the third hypothesis is that fast rotation caused the activity of A2. Fast rotation means it was rotating so fast, spinning so fast, that centrifugal forces could compensate the gravity of the object, at least at the tips and at the equator. This is consistent with the absence of fast ejecta because you would expect that velocities are just barely escaping. It is consistent with the planar ejection we found, which also the impact is unlikely to cause. And it is consistent with the presence of large debris. So to say a bit more about this, why was it spinning so fast? We have this yaw effect, which changes an asteroid's spin rate. The basic idea is that if you have an irregular body, the thermal radiation from the body is anisotropic. And thus the momentum radiated in different directions is different. So you have a torque exerted on the body. And this torque can change the spin rate or spin orientation of the body. And one possibility is that it actually accelerates the rotation of the body. So it can accelerate it to the degree that the body disrupts. And one indication that this actually happens comes from this plot. This is, again, each point marks one asteroid, and you have the rotation period of observed asteroids plotted against the effective diameter. And you see that there is a peculiar absence of asteroids in this region. So large asteroids that are rotating faster than 2 hours. And the interpretation is that the larger asteroids are rubble piles. So they are assemblies of loose material that are held together mainly by gravity. And that if they start to spin too fast, they just break apart. So this is why they do not exist. They cannot spin faster than with a 2-hour period. On the other hand, the smaller asteroids, they may be monolithic rocks. So they can spin much faster before breaking up. So this is both an indication that the rubble pile picture of asteroids is correct, and that this process of rotational breakup actually does exist. And now it may be that we are actually seeing this process happening, so that we see objects that come from here to there and then break apart. Another asteroid that is, in a sense, similar to A2 is this one, F5. It also has this very thin nucleus trail following a cyclone. It has fragments just like A2, but in addition to A2, it has a measured rotation period. A2 is so tiny with its 60 meters that we did not manage to measure the rotation period. This one is larger, it's on the order of 2 kilometers. So we have this rotation period, and it's about 3 hours. So that is not at the very critical spin rate, but it is possible that if the body is very elongated, which we don't know, that already at a 3-hour rotation period, material can be detached from the furthest points at the equator. So this is really something we would like to know more about, and we have proposals submitted to get more data. P5 is another very surprising object because it has multiple tails. When it was discovered, it had on the order of 6 tails pointing in different directions, and with changing geometry, the orientation of the tails also changed. And so this is the same image, only a bit clearer. And we find that each of these tails, again, corresponds to a synchrone. That's not surprising because you can always, if you have a straight line, you can always find a date that is the synchrone that corresponds to this angle. So this we did for the first image from September 9th. And this is the image from 2 weeks later, so with a completely different observation geometry. And again, we calculated the corresponding synchrones. And then we made a similar plot as we did for A2. And we find that for each of the tails, the 2 angles lie on the same synchrone. So each tail has a unique ejection date associated to it, which means that the asteroid was active in bursts. It was active and then it shut down for like a week or 2 or a month, and then again ejected some dust and then shut down again. And this happened 6 times, and this created the 6 tails. And we got even more data and followed it for about 6 months and found that the old tails dissipated, but new tails appeared. So we found that this intermittent activity continued for about at least 9 months. And then again, for this one, we got an image taken when the Earth was in the orbital plane of the asteroid. So basically, you see the dust sheet from inside. So it's a very thin line. This is HST. I think these are native HST pixels, so it's really very thin. And this allows us to derive the vertical ejection speeds of the dust. So only the vertical component, not the horizontal one, because the horizontal one is always interleaved with the radiation pressure, so you never know, which is the influence of which course. But the vertical speed is not influenced by radiation pressure. So the vertical extent allows us to directly constrain this velocity. And again, we find speeds on the order of 0.1 meter per second, which is below the escape speed from the nucleus. The nucleus is a bit larger, it's 240 meters. And again, we find these velocities that are very similar to the escape speed from the nucleus. So the question is the same: what caused this activity? And for sublimation, the arguments are similar to A2. It's very small, it's also in the inner asteroid belt. It is very unlikely that ice can be conserved in such a body. And also, it's not clear why sublimation would cause these type of bursts. Was it an impact? Again, we see the absence of fast ejector. These tails follow beautiful synchrones. There's no trace of any fast velocity ejector, and also an impact would not create intermittent activity. That would be one flash, and that would be it. So again, we think that rotation remains the most likely explanation for this type of activity. We have the absence of fast ejector, we have the velocities on the order of the escape speed. And the intermittent mass loss could be caused by landslides, for instance. So the material would slide towards the equator and cause a dust cloud, and then rotation would accelerate a bit further, and then another chunk of material would become unstable and again slide towards the equator. So that could be one model to explain why we have this repeated bursty mass loss. My next object is R3, discovered almost simultaneously to P5, but entirely different. So this is a time series over a few months. When it was discovered, R3 consisted already of 3 fragments, each of which had its own comet-like dust tail. And then we got HST data, which showed that actually some of the fragments consisted of more than 1 fragment. This is a graph, but this is a PEC image, so you couldn't see the individual fragments. But with time, you see that even more fragments appear and that the fragmentation was actually ongoing as we followed the object. And these fragments are not gravitationally bound. The whole sphere of the individual nuclei is much smaller than the distance we see. So we have this stepwise process of fragmentation. We have ongoing dust activity, so each of these fragments have their own tail, and if you stretch the image a bit further, then you see that there's also a tail in the other direction, which means that the activity has been ongoing for quite some time, like at least 2 months or 3 months. And again, if you look at the separations of the fragments and follow them over time, you can get an idea of the separation speed, and again it is on the order of the escape speed. Which leads us to think that sublimation probably was not the cause for the original disruption, but may have been the cause for the protracted ejection of dust later on, maybe because ice was exposed in the breakup. The impact is unlikely because it should not cause a successive breakup, and again because we don't see high velocity ejecta. So again, we think that probably also this one was a rotational breakup, and that in this object, the object really disintegrated entirely due to the fast rotation. There has been a theoretical study by now, studying different ways of asteroids to break up when they are rotating too fast. And indeed, it seems to depend very much on the original shape and of the material composition of the bodies, how they behave when they rotate too fast. So some of them break up in the center, like R3, and others just shed material from the surfaces, like P5. So maybe the same causes different ways of reacting to it. In summary, active asteroids seem immensely diverse. Each new discovery looks entirely different and brings new surprises, but some features do reoccur. And we have this group of main-belt comets with protracted mass loss and with repetitive mass loss, which we think is caused by sublimation of ice. Some active asteroids eject fragments, others only small material. The debris velocities typically are comparable to the escape speed of the nuclei, which make us think that rotation is somehow involved in the breakup. And we have the short rotation periods in those asteroids where we measured it. And even if the fast rotation does not cause the breakup, it reduces gravity and enables the asteroid to eject the material. So this is an attempt to put all the pieces together. We have the individual objects, but maybe there is an underlying topic that sort of comprises them. So the idea is maybe activity occurs, it needs a trigger. They have not been active since the age of the solar system, that's unlikely. Maybe the trigger is an impact or fast rotation. And this trigger causes the reshaping of the nucleus in one way or other. Maybe it's just landslides, maybe it's the ejection of fragments, maybe it's entire breakup. That depends on the initial conditions, on the shape of the asteroid, on the material strength. Whatever happens, the nucleus reshaping creates a dust cloud. And this dust cloud then results in this instantaneous activity we see in some of the asteroids. And in addition to the dust cloud, the reshaping of the nucleus may expose ice that was previously contained in the interior of the asteroid, and that now comes to the surface and starts to sublimate. And if that happens, you see the protracted activity and the recurrent activity that we associate with sublimation of ice. This might explain why in the asteroids that, in some just ice was not exposed, especially in the smaller ones. In some others probably yes. So maybe this explains the very different appearances. Yeah, but there's certainly a lot of work to be done to support this concept. Yeah, the perspective is asteroids definitely are subject to change. They are not the inert bodies that we thought of they are like 20 years ago. Fast rotation seems to be important in their breakup. Asteroids may be reservoirs of maybe primordial ice, and as such they may be important for the water on Earth, because there was a time when the giant planets moved in the early solar system, when asteroids were scattered around and lots of them hit Earth, which is called the late heavy bombardment. And if they were really full of ice, then maybe they filled our oceans. And finally, active asteroids are sources of interplanetary dust. They are filling the zodiacal cloud, and we should also take them, in addition to comets, into account for those models. It's the thermal re-radiation from the asteroid.
Why would it be so?
It's because if you have either an irregular shape or a different albedo, because it radiates different amounts of momentum in different directions.
But why is the effect of the Earth also rotated by half a year?
It depends. It depends on the shape. If it's a sphere, then it is reversible, then there's no effect. But if the effect is if the shape is very irregular, then there can remain a component that is not reversible, that always points in the same direction.
So did you, I think you actually mentioned it very slightly at the very end. Are there studies done on the albedo of the active compared to the non-active asteroids? And is there a difference in the surface of the asteroids that we know can be active at times compared to the asteroids that have never known to be active?
I think that we don't know the albedo of the active asteroids, because to measure the albedo you always need infrared observations.
But at least the first one you showed has been observed also in periods that it was not active.
Maybe it's known for them. If the albedo has been measured, then it is similar to the other asteroids. So, yeah, for most we don't know, but for some maybe we know.
And I was slightly surprised to see that the tails that work so well, because I mean, as you explained very clearly in the beginning, the balance of the radiation pressure and the mass of the grains works out as being independent of distance. But if I think of the grain as an ice mantle, and this ice mantle starts to slowly be removed from the grain, the ice is mass. It actually doesn't absorb very well. So actually I would expect that as a function of time, your grains would get lighter.
Yes.
And so I would expect that the tails wouldn't fit so nicely with your model, which assumes that the grains keep their identity as a function of time.
That is probably because the grains don't have ice. They probably are refractive dust. That's what you see in the comment. All the dust that you see in the tail is refractive. If there was ice, then it sublimates in the inner core and not in what you see in the telescope.
That's interesting.
But you're right that if there is ice and the melting of the ice changes the property of the grain, then also the beta parameter changes with time. That's correct.
Many asteroids are part of a special family defined by their chemistry or special orbital features. Do these fast rotators are also make up a family on their own?
They don't make up a family of their own. Some of them belong to some of the families, or probably belong to them. You can calculate it from the dynamics if they have similar orbits. So some of them, yes, they are part of one of the asteroid families. But they are not a family of their own. They're entirely different, independent objects.
And which is the most important of these families?
I don't know.
For example, these asteroid 2010 A2, where does it belong to?
I believe it belongs to the Flora family. But I would rather look beforehand.
Yeah, very similar question actually, because I think in the beginning you showed a figure with the radial distance of the asteroid belt. So so are these active comets rather found around the outer asteroid belt or in the inner asteroid belt?
Both.
Is both? Is it just completely random?
Yeah, it's not a specific, they don't have specific orbits.
Yeah.
This one. No, you actually find them two. There's another one which is not in the plot because the plot is from 2012. B5 is also very close to that too. They're in the inner asteroid belt. Most of them are in the outer asteroid belt. But you even have these near-Earth asteroids. This one, Phaethon, approaches the Sun by I don't know, a tiny amount.
But there are much fewer asteroids very close with small semi-major actors, so the percentage of active comets seems to be higher at closer ones because
Further out.
there you have many, so the percentage could dramatically increase with the closest to the Sun.
Good, yeah. I think we don't have enough objects yet to really be sure of this. Also because we have detection biases. Most of these objects are detected by the automatic sky surveys. So, before you do statistics, you really have to be sure that you account for all your biases. But you're right, most of them are in the outer asteroid belt.
You showed the plot with the diameter versus rotation speed. And you showed that there's more or less this forbidden zone, or zone of avoidance, whatever you want to call it. Is that theoretically supported? Are there models that predict exactly that?
Yes, I think there are models that calculate if you have a rubble pile of some assumed shape that 2 hours is the critical period.
And can you use these models also to kind of predict whether the signatures that you see, that you just described, these might also originate from breakup, or from partial breakup, so to say?
You can use the models, but you need more data. So for many of these asteroids, we don't know the rotation period, and we don't know their shape. And it critically depends on the shape. And this one I showed you, F5, is the first where I think we can probably do it because we already have one light curve. And if we get more light curves over the next years, we see it rotating from different perspectives. And this allows to calculate shape models of the asteroid. And then you can see, if you have the shape models, you know if the 3 hours are critical or not. So, but that's the next step. And for now, there's no object that has enough data to really tell us.
Assuming that the activity could be larger for asteroids closer to the Sun, I would suggest that in a few years we look at the data of the Gaia satellite, because Gaia has the possibility to look as close as 45 degrees to the Sun, and by that it should probably discover many new asteroids, and also will deliver photometry during all the observations. So you could even study the huge outbursts within the Gaia data itself.
Yeah, that would be really good. We're looking forward to that.
I guess I have a fairly naive question. Before I came here today, I thought what a comet is and an asteroid. An asteroid is a rock or a pile of rocks, and a comet is a dirty snowball. That was my mean square assumption. Now you show here this plot that comets and asteroids are distinguished by their orbital characteristics, and not so much by their internal composition. But nevertheless, my actual question is, are you now pointing to the possibility that there is no such a clear distinction, that there is basically a continuum of internal, different internal composition?
No, I wouldn't say so. Because comets, they haven't been there for a long time. They come from the Kuiper belt or from the Oort, from the outer solar system. And when they encounter the giant planets, then their orbits are changed and the comets are scattered into the inner solar system. So they haven't been there for a very long time. And they also won't stay there for a very long time because they keep encountering Jupiter. So their orbits are not really stable for really long time scales. Whereas the asteroids, they have been there for, I don't know, since the age of the solar system probably. And there's also, as far as I know, there are simulations that, or there's no simulation that found a dynamical paths from a comet's orbit to an asteroid's orbit. So, or to put it differently, a dynamical path of putting a Kuiper belt orbit into the orbit of an asteroid. So I think they are really different types of object.
Which kind of information are you getting out from probes which are orbiting around the asteroids or Rosetta?
There are unfortunately not so many probes that orbit around asteroids. Rosetta is in a comet, and we get all types of information, images, and spectra, and in situ data, seeing individual particles, so that's a lot. But for asteroids, there has been a sample return mission to one asteroid, not to an active asteroid, which tells about the material. They collected some material, so we can analyze the material. But there are not so many probes that go to asteroids, unfortunately. It would be cool. There are mission proposals for ESA to go to one of the active asteroids, but they are still in the very early stages of the proposal.
Very big ones or larger ones?
Yes, like Vesta and Ceres.
Just a different story.
I think they are a different story, yes. I mean, for Ceres, you have these images of Ceres because dawn just arrived there. And it has these white spots, and there's water vapor has been measured by Herschel. But Ceres is huge. For sure, Ceres is not rotating too fast to take material. So there may be common processes, but they are a different story.
What is the reason for the multiple tanks you have shown us?
The reason is the ejection at multiple dates. So each ejection day created a dust cloud, which was blown away by radiation pressure. And the orientation on sky just depended on the age of the tail.
This ice. Have to do some measurements of water. So gas line, or comets, of course, it's very common that you just find you see gas or evaporate ice.
There are no detectors of any gas species.
Yeah,
there are other ones, but they are all such that they don't exclude sublimation. So if you have a very tiny spot on the surface that sublimates, the amount of water vapor may be so small that you will not detect it. In particular, water vapor is very difficult to detect from within the atmosphere. So in comets, what you usually detect is CN, the CN molecule, and then you kind of assume that there is a certain ratio between CN and OH. But for asteroids, we don't know if the ratio between CN and OH will be the same. And also CN was not detected in asteroids. So, that's that. Even on R3, where we thought, we caught it in the act.
So there's no direct detection yet of ice?
No, it hasn't been.
If I look at the image of this, I don't know how to pronounce it, the chunks, and then as you rotate further, they start to separate until at some point they just fly apart.
Yeah.
Is this excluded, or could it be, or what's your opinion about it? Maybe it's a completely crazy idea.
No, but actually I cannot really answer it. I haven't heard anything that it's threatened to break up very soon. So also in comets, this yaw effect is not the driving one that accelerates the spin or decelerates the spin. In comets, it's the outgas. Because if you have an outgas, it's like a rocket engine.
Right.
It can really accelerate the body much faster, or also decelerate. So I think there are indications that the spin rate of Primordial is changing. Has been changing since the last iteration. So we have light curves from 7 years ago, and we have the light curve now. It seems to be a bit different.
All right, further questions?
Just a moment, is there reliable statistics about the rotation periods of the asteroid?
Of the active asteroids? Not of the statistics. No, there are only a few where we could measure it because many of them are just too small and it's very difficult to get time. You need like a VLT for this. So there's only a handful and I won't do statistics on that.
You talked in comments about the exclusion of or you didn't think that impact was the most likely.
Yeah.
Is there calculations of what we would expect for impact rates? I mean,
There are calculations,
and
yes.
so do you expect many impacts to happen in anything? Or?
I think we expect 1 to 2 impacts a year or something, but it depends on the size. On the smaller asteroids, we have more higher likelihood. On the larger ones, lower likelihood. And then you also have to calculate again your detection bias because you don't detect all the impacts. You have to have pan stars looking in the right direction all the time. So this is very hard to say.
But it's not a very rare event that something hits each other.
No, it doesn't seem to.
Just a follow-up on the statistics question, so to say. You stressed now a couple of times that you lack the information because the ones that you see are quite small and quite faint. Is there a correlation that it's primarily the small ones that become active? Can you draw that conclusion, or is it just?
We know that a dozen objects, or maybe 15 by now. So it's very hard to see correlations. There's one object that was much larger, several dozens of kilometers, Sheila, and this was clearly impacted, rotates very slowly. So yeah, also the bigger ones are impacted and you see them. But I think it's too early to make statistics.
But from a model point of view, are the small ones, do they have a higher chance to rotate up to their breakup?
Yes, they have, because this yaw effect acts faster for smaller bodies.